Stoichiometry is simply calculations that are used to relate amounts, usually in the units of grams or liters, of substances in a chemical reaction to each other. If we look at a very simple equation, and we balance it, there's a certain amount of information that's present in this equation. Okay, the equation tells us what are the reactants, the equation tells us the product that is produced, and the numbers here also tell us the ratio of atoms or molecules that are needed. So for example, this is 2 hydrogen molecules react with 1 oxygen molecule and form 2 water molecules. So we see that these ratios are very important. Right? If we look at these, okay, this is for every 2 hydrogen molecules, we only need 1 oxygen molecule. Or for every 2 hydrogen molecules, we're going to make 2 water molecules. The problem is that when we're looking at chemical reactions, we don't observe them. We don't observe them in terms of atoms. We look at millions and billions of atoms. We need observable amounts, and that's again the power of the mole. Okay? So we can look at this in terms of ratio of moles, not just ratio of atoms to each other. So if I take 2 moles of hydrogen molecules, I will need 1 mole of oxygen molecules, and I'll create 2 moles of water molecules. Well, why do we want to think about it that way? Well, when we do chemistry, we tend to measure things. These are measurable units for us. We can measure grams of something, or we can measure liters of gases. Okay, we can't measure moles directly, but the moles are needed because they reflect the ratio of the molecules to each other in a chemical reaction. So, when we do stoichiometry, we need a balanced chemical equation because we need the mole ratio, but we're going to start and end, okay, we're going to start with some amount of grams or liters, and we're going to want to know some information about grams or liters. So we're going to need to do mole conversions, and we're also going to need to use the mole ratios we find in our balanced chemical equation. Now the steps we're going to use to do a stoichiometry reaction can be remembered using this little mnemonic. D2, U, M2. I call this a dumb problem. D-U-M. Okay, the 2 reminds us I have to do D twice, and the 2 here, M twice. What does the D stand for? The D stands for divide. What does the M stand for? Well, the opposite. The M stands for multiply. And the U is going to stand for moving things from one to the other. So our first D's are we are going to divide the starting amount by molar mass. And the second D, then we're going to divide the answer by the coefficient. Now remember, in chemistry, a coefficient is the number that appears in front of a formula in a balanced chemical equation. Okay, the U stands for move under. So we're going to start talking about one thing in a balanced chemical equation, and then we're supposed to be finding out an amount of a different thing in the balanced chemical equation. And the U just reminds us is that we're going to switch from what we're starting with we're going to move under what it is that we're supposed to find out about. Okay, the M's stand for multiply. Okay, so now we're going to multiply by coefficient, but it's going to be a different coefficient because we're going to switch from talking about one thing to talking about something else. And the second M is multiplied by molar mass. Okay, so we're going to do a couple of examples of these so you can see how you work through these steps. It's very important. A couple of things are very important. First of all, make sure that you always show all of your work in these problems if you want all the credit. If it's a compound and you need to find the molar mass of the compound, you need to show me the work for finding the molar mass of the compound. You need to show me dividing by the coefficients and multiplying by coefficients, even if the coefficients are 1. Alright, so let's go to our first example problem here. Okay, so here we have a chemical equation. It is unbalanced, so that's the first thing we're going to need to do. And then we're going to find the number of grams of aluminum that we're going to need if we want the reaction to produce 50 grams of aluminum oxide. Alright, so let's balance our equation first. Okay, the O's are balanced. Okay, the FE's, I'm going to need 2 FE's. And I need 2 aluminums. Okay, now that I've balanced my chemical equation, I now have a coefficient to go with everything in the reaction. The 2 for aluminum, 1 for Fe2O3, a 2 for Fe, and a 1 for Al2O3. Now, we're going to remind ourselves that the steps are D2U M2. Okay, now when you start the equation, you want to look for the number, because that's where you have to start. It's 50 grams, and it's going to be of something. In this case, it's aluminum oxide. So you have to go and say, we're going to be starting here. So everything that we do for the first 2 D's is going to have to do with this particular formula. Okay, remember the first D, D1, is to divide your starting amount, which is 50 grams, by molar mass. So we need to find the molar mass of Al2O3. So I'm going to put that over here. So I have 2 aluminums and 3 oxygens. Okay. Alright, time to fire up the calculator. So I've got 26.982 times 2, and I'm going to add that to 3 times 15.999. Okay, and that's going to equal 101.96. Okay, remember I have 5 significant figures. Okay, so that means I have to divide the 50 grams by 101.96. This is the molar mass of the aluminum oxide. So 50 divided by 101.96 is 0.49. Okay, D2 says I divide the 0.99, it's going to be 0.49, by the number in front of the formula, which is, since there's nothing there, that's a 1. So 0.49 divided by 1 equals 0.49. I know it may seem kind of funny to have to show me the work for dividing by 1, but it's really good for me to show, you need to show me that you're remembering what you're tracking. Okay, so what we're doing here is we're converting these to the number of moles, say, and then we're starting to look at the ratio between the aluminum oxide and what the other information is that we need, what we're trying to find out about. Okay, so now we're going to do the U part. The U part, remember, is move it under from aluminum oxide. Now we need to go back to the problem and say, what is it that we want? We're supposed to find grams of aluminum. Here's the aluminum. Okay, so the U part is we're going to go to aluminum now. Okay, I'm going to switch pen colors here. Now we're going to do the multiplication end. Okay, so we divided twice, now we're going to multiply. Okay, so remember, the first multiplication is you take your answer from here, which is 0.49, and you multiply it times, now we're working under aluminum, the number in front of the aluminum, which is a 2. And that's 0.98. Okay, the M2 is we're going to take the 0.98, and now we're going to multiply the molar mass of this. Well, that's just aluminum. So that's 26.982. And the answer is 26.4633. Now remember, you have to round off your answer to significant figures. So you go back here, this is the starting number, 50. This is not a significant zero. Remember, zeros at the end without decimal points are non-significant. So there's only one significant figure. So how do I round this off to one significant figure? Okay, well, I can remember, if you're rounding, you can just drop off the ones after the decimal point, just get rid of them. When you go over and you have before the decimal point, you have to replace them with zeros. So this is going to become a 0, so the question is, do I round this to 20 or round this to 30? So this is going to be 6, so I'm going to round it to 30 grams of aluminum. Okay, let's try another problem with that. Okay, here we have another equation. This says find the number of grams of carbon dioxide produced when 7.2 grams of sodium bicarbonate decomposes. Alright, so here's the starting information, 7.2 grams of sodium bicarbonate. Look at the equation and say, where's the bicarbonate? Right here. This is the sodium bicarbonate. Alright, this is not balanced, so we better do that real quick. Okay, we'll put a 2 here. I need 2 NAs, so that gives me two carbons, which now I have. Okay, and this gives me 2 times 3 is 6 oxygens on this side. I've got 3, 4, 5, 6. Okay, so that was pretty easy to balance. Now remember, this is a dumb problem. Alright, so I'm going to start here with the 7.2 grams of sodium bicarbonate, and the first division, remember, is divided by molar mass. So I need molar mass of this. Okay, well, I've got 1 Na, it's 22.99, 1 H, which is 1.0079, 1 carbon, 12.011, and 3 oxygens. Okay, I'm going to add all of these up. Sorry. And let's see what the molar mass is. Okay, my calculator says 84.006. Okay, that's the molar mass of the sodium bicarbonate. Okay, so I'm going to take the 7.2 and divide it by 84.006. Remember, this is D1. It's the first division. Okay, so 7.2 divided by 84.006 is 0.0857. Okay, second division is my answer over the coefficient, the number in front of the formula, which is 2. So divide my answer by 2, and now I have 0.0249. Excuse me, 0.0429. Okay, I'm going to move it under. So now I'm going to stop worrying about sodium bicarbonate. Now I'm going to go and say, okay, what am I supposed to find? I'm supposed to find grams of carbon dioxide. That means I'm going to move to here. Started here, moving to here. Okay, so I'm switching to CO2. Alright, so now it's time to do the multiplication. First multiplication is I'm going to take this one answer, 0.0429, and I'll multiply it by the number in front of the CO2. There's nothing there, which means 1. Okay, the second multiplication, remember, is the molar mass. See how it's molar mass coefficient, and then it goes coefficient molar mass. Now I need the molar mass of CO2. Alright, well I've got one carbon at 12.011 and 2 oxygens at 15.999. This is 44.001. So I'm going to take 0.0429 times 44.001. Okay, in this case the answer is 1.8856. Okay, now I'm going to go back here and say, how do I round that off? I have 2 significant figures, so I need to round this one off to 2. Okay, so that disappears, that disappears, that disappears. Okay, that, since that's an 8, I'm going to round that to 1.9 grams of CO2. Okay, lots of math. Not difficult math, you just have to remember what are the steps and what order do you do the steps in. Alright, one more problem, because we have to talk about something that's sometimes called mixed stoichiometry. Okay, let's go back here real quick. Mixed. What do I mean if I talk about mixed stoichiometry? That means the units that are at the beginning, the units, not the number, the beginning and the end of the stoichiometry problem are different. Okay, in our previous problems we've been starting with grams and ending with grams. So this usually is liters to grams, or when you start to grams and you end with liters. Now, the key, if you have liters, is you will substitute 22.4 instead of molar mass. Because remember, anytime we're doing these multiplying and dividing with molar mass, we're converting from moles to grams or grams to moles. For liters, we don't use molar mass. We use the fact that 22.4 liters is the volume for 1 mole of any gas. So when we will still do the same steps, we'll still do the divide, the move it under, the multiply, but the first D and the last M, okay, we have to look very carefully now. We look at the unit. If we start with liters, the first D will be 22.4. If we end with liters, the last M will be 22.4. Let's look at an example of what I mean by that. Alrighty, so here's an equation. I've already balanced it out for you. And it says, determine how many liters of oxygen gas are needed to produce 175 grams of water. Please note the units here. This says liters. This one says grams. Alright, so we're going to do the same problem. We're going to start with 175 grams of water. Here's the water right here. We're going to start here. Okay, so the D1 is to take the 175 grams and divide it by the molar mass of H2O. So I have 2 hydrogens at 1.0079 and 1 oxygen at 15.999. Okay, that's going to be pretty darn close to 18. 18.015. Now this looks the same as the first example problems. Okay, so we'll take our 175 and divide it by 18.015. Okay, and that is 9.71. D2 is going to be the same. We're going to take the 9.71. Remember, D2 is the coefficient, and we're going to divide it by the coefficient here, which is the 18. And that's 0.54. Okay, we're going to move it under. Now we go back here, and we say, what do we move it under to? What am I finding? I want to know how many liters of oxygen gas, so I'm going to move here. So I'm going to move under to O2. Now, remember the first multiplication is the answer, the last answer you got, times the number in front of the formula. So this is times 25. Okay, and this is 13.5. Now, since it is liters, M2 is going to be the answer times 22.4, not molar mass. Why am I not going to use the molar mass this time? Because the unit I want is liters. If it was grams, I would use molar mass. I don't have grams, I have liters. So I'm going to just simply multiply the answer by, we're going to put 22.4 instead of the molar mass. Okay, 302.22. Okay, now I ask myself, how many significant figures do I round to? I have 1, 2, 3. This has to be rounded. So I'll just drop off the 2's after the decimal point. 302 liters of O2. Now, if liters had been here, I would have used 22.4 instead of molar mass. So that's the only trick you have to remember. You just have to stop and check very carefully and say, well, what's the unit? If it's grams, molar mass. If it's liters, substitute 22.4 in place of molar mass for that step. That's it.